Girls, let's choose a color. Choose a color. Pink doesn't show up well on the screen. Yellow also doesn't show up well. Black. No, but this lady at the front has been insisting, let's go for black. Classic. Black is classic. Goes with everything. Here we go. Triple integrals. Okay. Could you please keep quiet? Could you please keep quiet? Okay, now, if you don't know anything about calculus, or if you do know some single variable calculus but no multivariable calculus, triple integrals look like the most intimidating kind because they've got 3 integral signs, so surely they must be 3 times as hard as a single variable integral. Triple integrals are really no big deal. Once you've got the hang of double integrals, once you've got the hang of thinking of multivariable integration at all, then triple integrals and double integrals are the same level of difficulty. It's surface integrals that are trickier, which is something that you don't recognize when you're a bit of a novice at this stuff. Triple integrals are really no big deal. The only tricky thing in triple integrals is describing your region, because it'll be a 3-dimensional region, and the description of your region is what's going to go as your limits of integration. So that's the tricky bit. But otherwise, it's fine. There's no weird things like the conversion factor in surface integrals, or projecting on anything, or what else? Flux has those normals. There's nothing weird like that. It's just straight up, nice and easy integral. So let's have a look. Basically just putting triple integrals into perspective in the sort of family of integration. An integral of a function of a single variable. Remember those halcyon days back in first year when you thought single variable integration was tricky? Sure. How young and naive you were then is evaluated. The integral of a function of a single variable is evaluated over an interval x, or whatever your variable happens to be called, between a and b. An integral of a function of 2 variables is a double integral over, I'm not going to say a region because we use the term region for 3D as well. I'm going to be quite explicit here and say over an area, so basically a 2-dimensional region, R, on a plane, frequently the xy plane, an integral of a function of 3 variables, I'm just going to write VARs, variables, is a triple integral. I just abbreviated variables there because I was running out of space on the page. It's a triple integral over, again, you would normally say region, but just to emphasize the dimensions, I'm going to say over a volume in R3. Although we still do often just call it R, although we still often call it R for region. So that letter R is not only used for 2-dimensional regions. Okay, and a triple integral is basically a triple sum. So integral of some function of x, y, z dv is equal to the limit as L, M, and N all tend to infinity of a sigma, a sigma, a sigma. I goes from 1 to L, J goes from 1 to M, and K goes from 1 to N. So basically what you're going to do is you're going to divide your 3-dimensional region up into little bricks. You're going to take a representative point in each brick. You're going to number them according to what I've written here. You're going to number the sort of x divisions, the divisions of your little bricks that are parallel to the x-axis. You're going to number them and count them up as I, and parallel to the y-axis you're going to number them, and you're going to use j as your counter, and then vertically parallel to the z-axis you're going to number your little bricks, and you're going to count them up using the counter k. So in any one brick you'll have a representative point x, i, y, j, and z, k. You're going to evaluate f, whatever f is, in that little brick. You're going to multiply, I was saying k, and so hence I wrote k there. That's delta v, excuse me, delta v, there we go. And you're going to multiply by the little volume of the brick. And then whatever f is measuring, you've now got f times delta v. You got that quantity evaluated for that little brick, and then you're going to add it up for all the little bricks. And then you're going to allow the number of little bricks to tend to infinity, and their length, breadth, and height to tend to 0. And so you're going to end up with whatever f times v is. Okay, so that over there is a representative point in each little brick. Representative point in each brick. And this triple integral is evaluated over our region, which we're calling R. There is no, for double integrals, we usually call our region either R for region or D for domain. So, I mean, you can call it anything, but those are the two typical names that we call our region. In triple integrals, there isn't really much of a convention. R, yes, for region, rarely D for domain, but you'll also find problems here where we've called it B, or we've called it E, or it's just a name for the region. Question? Point, yes, my beautiful handwriting. I've never won any awards for my handwriting. I wonder why. Here we go, point. Slightly more readable, yeah?
This f, like our function, is it going to be something like a plane that's just got, or not a plane, but anything that's got 3 variables? And
yeah, so f is some quality of the objects. So a typical one that we use in our various things is density. And here we're back to classic density, volume density. So f would typically be something like density, which you then times in by volume to get mass. So f is some function of x, y, z. It's not a surface or anything. F is some quality of the three-dimensional object. And then depending on what that quality is, that triple integral will give you some hopefully meaningful result.
so we're not going to have physical functions, basically.
Well, you'll have your surfaces, and your surfaces will give you your shape of your region, which will hence give you your limits of integration.
Yeah, but so I mean, in the function that you're differentiating, it's not going to be a physical, like a surface or something. We
Correct.
can see in 3D space.
Correct. The actual integrand will not be anything structural. Yeah. Okay, volume R is divided into L by M by N little bricks of volume delta V equals delta X, delta Y, delta Z. Okay, so it's very like double integrals. We're just adding in one more dimension. Surface integrals are a different animal again, but triple is basically just adding one more dimension to double. Okay, so triple integrals, just like double integrals, can be solved iteratively. Triple integrals, just like double integrals, can be solved iteratively, where the most complicated situation would be, and it'll look like this. So this is as complicated as it can get. Okay, so over here I'm just writing my basic non-iterative integral. Now I'm going to put in some limits of integration. The outside integral is just going to have numbers on it. The middle integral can have functions of the variable that's yet to be integrated. And the most inside, the first integral sign to get a go, do I want to use a U, H? I wonder why I used G. Let me go for H. H1 of xy, H2 of xy. Okay, I'll talk about what I've done. The way I've written it here, z is going first. Okay, z is going to be the first integral with respect to which I will integrate. The limits of integration can hence have x's and y's in them, because x and y are yet to have their turn. So when I integrate with respect to z, and I say, okay, what did I differentiate with respect to z to get this thing, and I anti-differentiate, and I draw my little square brackets, and I put my limits of integration there, it's okay to be introducing x's and y's, because x and y are still coming up. Okay, cool. But now, when I finish doing the z integral, there's no z's left. There's just x's and y's. Then I'm integrating, according to the order I've written here, with respect to y. Okay? So the limits of integration can have x's in, but they can't have z's, because z's done with. So, but they can have x's, because x is still to come. So I can have functions of x as my limits of integration, and then by the time I get to my very last one, which in the order I've chosen to write is x, I have to have numbers, just plain old numbers. Of course, this order here is not set in stone. It could be any order. Could be a different order. Actually, you know what? I'm going to choose a different color for these little notes I'm about to write here. So it could be a different order. Limits of integration would change accordingly. Okay, and then what am I writing here? So your first integral sign, the one on the inside, the limits of integration are functions of at most 2 variables. And then the next one, the limits are functions of at most 1 variable. And then the last one to go will have constants. Okay. And it's finding those limits of integration that are the big deal. The actual integration, whenever you're integrating, you only ever integrate with respect to 1 variable at a time. So all integration is, in a sense, single variable integration. It's setting up those limits of integration that are the hard, that is the hard part. Yes?
That what you wrote in the red, is that the fixed form? Like it must have at most 2 and at most 1 variable.
Yes, but at most, of course, means it could be less. Yeah. Okay, in a similar way to double integrals, applications include volume and mass. And volume would look like integral over R1 dV. Okay, and then mass, integral R. Oops, a daisy. What happened there? Is the mass of R. Where that integrand there is the volume density, which is what we tend to think of as density, because most things in this world do have volume. Okay, let's jump into some examples. Okay, I've got 38 here, but 38 is pretty easy. It says evaluate integral x, y, z squared dv, where r is the rectangular box given by x lies between 0 and 1, y between -1 and 2, and z between 0 and 3. It is just a rectangular box, so the limits of integration are simply numbers for all of them. I'm just going to go in alphabetical order because why not? So x is 0 to 1, y is -1 to 2, and z is 0 to 3. No trouble setting up the limits of integration. Now, if you call me over and you say, have I set up my limits of integration correctly, and I look at your integral signs and all I see is numbers, and I know that your region is not a rectangular box, then I can say, no, you haven't done it correctly without even reading the details. Because as soon as all 6 of your little limits there are numbers, you're describing a rectangular box. So if your region is curvy in any way, that curviness gets reflected in your limits of integration with a function somewhere along the line. Okay, easy peasy. What did I differentiate with respect to x to get this? That's a half x squared, evaluated from 0 to 1. Okay, I'm going to pause here and show you a technique for doing these things a little bit faster, which I have mentioned before, but I'm going to mention again. Notice how the x, the y, and the z are all just multiplied by one another. Okay, my integrand consists of a product of 3 factors, where each factor is a function of a single variable, x, y, z squared. And my limits of integration are all numbers. So when I integrate with respect to x, and I plug in that 1 and that 0, I'm just going to get a number which I can pull out. It's going to be the same story when I get to y. It's going to be the same story when I get to z. My 3 little factors here are being integrated completely independently of one another. They're having no effect on one another. I can actually integrate them simultaneously. I can get half x squared going from 0 to 1, half y squared going from -1 to 2, and a third z cubed going from 0 to 3. Now this is kind of ninja calculus here. So if you think I'm not confident I'm going to be able to recognize when I can do them simultaneously, then rather don't, because you don't want to make a mistake with this sort of thing. Okay. The key tells are that the integrand is just a single term which can be expressed as a product of functions where each of those functions is a function of a single variable only. Okay? That's one major thing. The second major thing is that all the limits are numbers. So when I integrate with respect to x, I'm not going to be introducing any more y's into the story. The y's that are there are the only y's I'm going to get, etc. Okay, so in this case it is okay, but yeah, there you go. That's all I can say. And that'll also, let's have a look, what'll that be? That'll be 4 over 2 subtract a half. And that'll be 27 over 3, 9 minus 0. 2 minus a half, that's 3 over 2, so it'll be 3 over 4, so it'll be 27 over 4. Go. Okie doke. So that was a very easy example. I'm glad it gave me an opportunity to demonstrate that though. I'm going to do a page jump. Okay, 39. So 39 is a little bit more complicated because it's not a rectangular box anymore. Evaluate integral z, where R is the solid tetrahedron bounded by the 4 planes x equals 0, in other words the yz plane, y equals 0, in other words the xz plane, z equals 0, in other words the xy plane, and that funny oblique plane, x plus y plus z equals 1. If I draw that picture, always draw a picture. Always draw a picture. Always draw a picture. And now people are going to come up to me and say, what have I done wrong? And I'm going to say, where's your picture? Don't be that person. Okay, that's the plane that I've drawn there. It's the oblique plane x plus y plus z equals 1. And now I need to integrate that integral. So I need to come up with my limits of integration equals. Okay, I'm going to leave gaps because sometimes my limits of integration can be quite chunky. Okay, all right, let's fill in the blanks. So my sort of personal visual way of figuring out how to describe limits of integration for three-dimensional objects is I think of my object as having a base, a two-dimensional base and a height. Now that base is not necessarily on the xy plane, it depends on my shape. But I'll decide, okay, my shape looks like whatever. I'm going to take one of those faces, preferably a face that's against one of my planes. I'm going to take that as my base, and then the remaining dimension will be my height. And then height always goes first. Height gets integrated first, and then the base, I back away to a double integral. Okay, so this shape here is very symmetric. Doesn't really matter which of those triangles on my coordinate planes I take as my so-called base, because they're all going to look the same. So I'm going to be fairly classical here, and I'm going to take the triangle on my xy plane as being my so-called base. Okay, those two variables there, x and y, they're going to contribute the last two variables to go. Z is going to go first. Z goes from the base to the opposite side of the region. So Z is going to go from my xy plane up to the top of my shape. And the top of my shape is that oblique plane. So Z is going to go from 0, so Z is going first, from 0 up to the oblique plane. What is the oblique plane? One minus x minus y. Okay, so Z goes from the base, which is Z equals 0, to the far side of the shape. And the far side of the shape is that oblique plane. Okay, the next two variables that are going to be these two. And now I don't need to look at my 3D picture anymore, I just need to look at this picture. So in a sense, I'm dealing with a double integral in a sense. Dealt with the one. And so I'm going to let y go first out of x and y, and y is going from the x-axis, y equals 0, up to that oblique line. What is that oblique line? That oblique line is y equals 1 minus x. So y is going from 0 to 1 minus x for values of x that go from 0 to 1. That's the integral that I'm solving. Okay, and then the actual integral is no sweat. You only ever do one variable at a time. Z, so it's going to be our half z squared evaluated from 0 to 1 minus x minus y. See, now this one, you can't do all the variables simultaneously, because see how integrating with respect to z is introducing x's and y's. So if I had rushed to integrate with respect to x and y before now, I would have missed information, if that makes any sense. Okay, so what is that? I'm going to pull the half out. I'm going to square 1 minus x minus y, and I'm going to get 1 plus x squared plus y squared minus 2x. I'm not used to squaring trinomials. Not used to squaring trinomials. It's hard. What do I got here? Oh, hey, hold on. That's interesting. That's interesting. I don't actually have to square it to trinomial. When I was typing up my solutions, I'd obviously had my pronutro, and I'd realized that actually just leaving it like that is sufficient. Yes, you can totally square it out. Nothing wrong with squaring it out. But you don't have to square it out. Because when you ask yourself, what did I differentiate with respect to y to get that, you can actually answer that question. You would say, I differentiated that thing there you go. Because if I differentiate this thing in the square brackets with respect to y, chain rule says that I first differentiate the outside thing by bringing down the 3 and subtracting 1. And so that'll get rid of the third. And it'll turn that 3 into a 2. But then chain rule says I still need to multiply by the derivative of the inside function, so I get a minus 1, which is what the minus is. Unless I've done something careless, I think that that is correct. Okay. Let me bring that minus a third out. What's that now? That's going to be 1 minus x minus 1 minus x cubed minus 1 minus x minus 0 cubed dx. Okay. Let's have a look. I don't actually need the brackets anymore. It's 1 over 6 times minus 1 over 4 times, put in a 1 and it's 0, put in 0 and it's minus 1. Is it minus 1? Is it 1 over 24? Yes. Okay, so there's a lot of minuses going on in this problem. There's a lot of negatives, and in some places I chose to pull them out of the integral signs, in some places I didn't. Pretty sure my answer is correct. Question?
Doesn't chain rule make that positive 1 over 4?
Yes, except that I pulled that minus out. I pulled that minus out. So, as I said, there's a lot of minuses going on in this problem, and in some of them you can even absorb some of them into brackets. So, yes. In some places there's a minus times a minus times a minus. Okay, all right. Now, according to my sort of schedule, let's have a look. What is the time? I have assigned question 40 for you to practice in class now. Now, question 40, the integrals have already been set up for you, so it's simply integrating. I know some of you have spent your holiday studying maths. I know that because you've been mailing me about it. Some of you probably haven't, so maybe a little bit of practice getting back into integration is a good idea. Question 41 I've assigned to the tutorial, but it's a more classic triple integral because you have to actually come up with your limits of integration yourself. Notice how they're calling the three-dimensional region E and that problem. Let's have a look. I see in 46 they use D, and 47 they use B. Yeah, there's no real convention. Okay, so why don't you give number 40 a go? Or if you want something a little bit more challenging, you could try 41, which is actually a TUT question.